Hi class, welcome to the next section in chapter 12, chapter 12.2. Today we're going to talk about doing calculus with parametric curves. So remember that a parametric equation it's still an equation, right? We're just taking the standard form of an equation and we're able to represent it now with a parameterization, right? X is a function of t, y is a function of t, right? So it's the same, it's still a function, it just looks different. Okay, where the way that we analyze it is different now. So this means that all of the things that we do in calculus is still applicable to a parameterized equation, right? A parametric curve. So let's talk about some of the applications of calculus that we've gone through Calc 1 and Calc 2 so far, and how to apply this to our parametric curves. So first we'll start with tangents. So let's say we have our function y equals f of x. Um, the derivative of that is differential of y over differential of x, right? Or generally dy dx is what we call it in the Leibniz notation. So if we now have a curve that's parameterized, right? Y is a function of t and x is a function of t. We're just going to differentiate those functions y and x in t separately, right? So the derivative dy dx is the function y in terms of t being differentiated with respect to t, and our x of t function being differentiated with respect to t as well. Okay. My bottom function, my x prime of t here, cannot be 0 because it's in the denominator position, right? So if you think about this, really what we're doing is we're dividing the numerator and the denominator both by dt because now you know, um, we have a new dependent and independent variable, right? To use independent variable for our dependent variables x and y. So if we want to use the standard prime notation for this, our y prime with respect to x is going to be dy dx or dy over dt over dx over dt, which we can simplify to y prime of t over x prime of t, right? So if I want to differentiate y with respect to x, using this notation, this Leibniz notation, we can turn it into a simpler prime form. At least for me, I prefer to look at the prime forms of things. So I'm taking my y function of t and I'm taking its derivative and I'm dividing that by my x function of t, its derivative. Okay, that derivative with respect to t for the x function cannot be 0 since it is in a denominator position, right? Now, if I take the second derivative, okay, of y with respect to x. Um, so again here we're basically playing with the algebra. My d over dt, this is the derivative with respect to t of dy. If I were to throw this across, look what I would have. I would have a d squared y on top. I would have a d squared tx on the bottom, but this dt and this dt cancel, and I would have my dx squared here on the bottom, right? So remember the way that this works. The, the derivative with x squared here. But I'm dividing the numerator by dt and the denominator by dt here. And so taking this Leibniz form, we can look at what that looks like in terms of our prime form. And so I'm basically just taking what I had before previously from the first derivative, and I'm going to differentiate that with respect to t, just like normal. I'm not doing any product rules or um, quotient rules. Just whatever the form looks like is what I'm going to differentiate. So if the form comes out to be nothing cancels, for instance, right? And we have a not a radical, a rational function, then yeah, I'll you go ahead and I'll differentiate that rational function appropriately by using the quotient rule. Okay. And so on my denominator, it's just the x differentiated with respect to t. Okay. So I'm not taking this and doing the quotient rule and saying, boom, now that's my second derivative, right? Or even taking the second derivative of the numerator and the second derivative of the denominator like you think we would do because that's what we did for the first derivative, right? So the Leibniz notation helps us understand how we need to actually differentiate this. So that's why it's very useful at times. Plus, we break it apart when we're looking at the differentials, especially when we're doing the differential equations, right? We need to break apart this dy and dx for the separable equations. So these things, the Leibniz notation is important, right? Um, and so yeah, so what I'm going to do is I'm just going to take, again, the previous result I got from the first derivative, and I'll just differentiate it with respect to t. Straight across, whatever form it is how I differentiate it. And then the denominator I had previously will be my new denominator. I'll divide that whole result by that same denominator, x prime of t. Okay. So this section we're going to go a little bit different. We're just going to show the rules, and then we'll do an example of each one. Okay. So that was what the tangents look like, right? The first derivative and second derivative have these forms. For the following definitions, we're going to be integrating, so we're going to assume that our curve is parameterized, right? Our curve being called C, and its parameterization is given by x of t and y of t, and this is through the angles alpha to beta. Okay, so here we're going to say that our curve is traversed exactly one time as I go from alpha to beta. So this, because of the way that parameterizations work, if I have a graph that is connected, right, like a circle, ellipse, or something like this, the bigger my range for the angles, the more times I traverse that object, right? So I can go around a circle 100 times if the angles are big enough, right? So here we're just assuming that we're going over once from alpha to beta. Okay, so the first thing we'll cover is an area. So the area A under our curve C is given by the integral from alpha to beta, y of t times x prime of t. Okay, and so basically what we're doing is, if you look at this, this really looks very similar to what we would have for um, integration by parts, right? Where we have a function and its derivative, and then we're looking for which one we're integrating, which one we're differentiating. So the same substitution that we would use to kind of um, talk about forming the formula for integration by parts is how we got here. So I'm not going to go through the derivation because it's literally just one step. That's not important. So if you want to look at how we found this, you can go to another textbook. Try to keep our derivations for things that come to interesting results. And we will be deriving other formulas. So this one, I'm just going to say, hey, this is this formula. Okay. Same thing for arc length. The length L of our curve C is given by the integral from alpha to beta, square root x prime squared plus y prime squared. Okay, and again, this just falls out from parameterizing the formula for area, right? This is basically what happens when we um, parameterize our function. Okay, surface area we know has the length formula in it, so this is going to show up again. So if x of t and y of t are rotated about the x-axis, then the surface area of that revolution is given by 2 pi times the integral from alpha to beta, that y function, and then the length of that curve, okay? Which is really just piece for piece the same thing for our standard surface area integral, right? It was 2 pi y times the length. So this should be pretty obvious once you know what the arc length formula is, okay? So let's go ahead and do an example. So first we'll start off with something that has to do with tangents. We'll kind of go in order. So we'll start with tangents. We'll do an area example, and then an arc length example, and a surface area example. Okay. Actually, I believe we just do a surface area since arc length is kind of incorporated in this formula. So we just do a surface area example. So our first example has to do with tangents. So we want to find the equation of the tangent line to the curve that is formed by x being t times cosine of t, and y being the function uh, t times sine of t at t equals pi. Okay, so we're going to need the derivative of this curve, which we just talked about, at this point, right? And then once I have the rate of change at that point, then I can take my input and output, my x and y values at that point, and find the equation for a line, right? So everything we're doing is the same thing we would do normally. It's just now we are in um, our curve is parameterized, right? So the first thing is I need to find the derivative. Remember, the derivative was the derivative of y with respect to t over the derivative of x with respect to t. Okay, so x prime, right? We're going to use the product rule here. So this goes to 1 times the function. Um, then we add just t and change this to negative sign, right? Since the way I remember cosine starts with a c, so it changes sign. So that's why we have a negative t sine t here for x prime. Next, we differentiate y, so it's the same thing. We're going to get just sine of t plus t cosine of t, okay? Because sine stays the same sign when we differentiate it, right? So t goes to 1 times the first function plus the first function stays the same, and then we differentiate the second one, right? So that's my x prime and my y prime. In order to find the rate of change at this point, I throw this on top of that, and then I plug in pi everywhere, right? So dy dx is going to be my y prime over my x prime, okay? At t equals pi, I plug that in everywhere. So for pi, for sine, we are at uh, 0. Cosine, we are at -1. This is pi. Cosine is -1 minus pi. Sine of t is 0. So this goes away, and then really I'm just going to be left with pi. Okay? So the rate of change at t equals pi is pi. Okay. Now, what is my x value at pi? Well, I plug that in. I'm going to get pi times, so this is -1, so that's negative pi. When I plug that into y, I'm going to get pi times 0, so that's 0. So the point that I have is negative pi, 0, and at that point, the rate of change is pi, okay, which I got from this derivative. So now I have a point and I have the rate of change at the point, so I can find the equation of a line. Remember, the equation of a line is y equals mx plus b. The reason I can use y equals mx plus b is because I have the actual values of x and y at this point and the actual rate of change at that point. So this is x and y now. This is not in any kind of other form. So y equals mx plus b. I solve for b. Okay, and I'm going to get pi squared. So then when I throw that all together for my tangent line, okay, I get my, the line is uh, mx plus b. So that's my tangent line. Okay. Let's do an example with the second derivative because the formula can be a little bit hard to follow. So let's go ahead and do that. So if we just kind of go backwards, okay, the formula for that is to find the first derivative using the parameterized version, and then differentiate that with respect to t, and then just throw it all over your denominator. So let's go ahead and go through that. The second example. Okay, so we want to find the second derivative for the curve that is formed by x equals e to the t and y equals t e to the negative t. So the first thing we have to do, very similar to this, is find the derivative for this curve. So I'm going to differentiate y, I'm going to differentiate x, and I'm going to put the derivative of y over the derivative of x. Again, both of those I'm differentiating with respect to t. Okay. So for x, very simple. It's just the derivative is its own function, right? So that's e of t. For the second one, we're going to have to do the product rule again, right? So I'm going to get e to the negative t as a common term on both sides, so I can go ahead and factor that out. Okay. All right, so I pull out the e to the negative t. There's 1 here and t of them left. I'll keep the negative sign. And so this is my form for y prime. Now, in order to go ahead and find the derivative, right, I put this result on top of this result, right? And so then what happens is that that simplifies, right? This e to the negative jumps down to the bottom with the e of t, so I have e of 2t, and I'm left with the 1 minus t on top. If you don't like that, you can just say, okay, we'll have e to the minus t, and I'm minusing another t, right? So that's plus a negative, so then you get two negatives, which is the same as having one on bottom, right? So this is my my derivative of y with respect to x, okay, for the parameterized curve. Now, in order to find the second derivative, I'm going to differentiate this again as is, right? It's not x and y again. It's just this result. Differentiate with respect to t and throw that result over when I got here for x prime, which was e to t. So I have this 1 minus t over e to the 2t, which I'm going to find the derivative of. And so here I'll use the quotient rule, right? So I differentiate the first function, um, which is 1 minus t, which will give me a negative 1. And I multiply that times the bottom function, okay? And then to that, I will subtract the first function being left the same and differentiating this bottom function. I divide that by the bottom function squared, okay? And so this is me just simplifying this term now, right? And so what I'm going to do, I notice I have an e to the negative t in two places, right, in both terms. So I'll factor that out. That leaves me a negative 1 on top, okay? And this 2 is being multiplied here. So I just moved it to the front, and I have my 1 minus t. Okay, I simplified the denominators. That's e to the 4t. Notice that those two things will cancel out, and I'll be left with an e to the 2t on the bottom. And then I can just do my arithmetic here on the top, right? So I have a negative 1 minus 2 and then plus 2t, right? So then that leaves me with negative 3 because I got minus 1 and adding to that another negative 3, and then this distributes to the t, okay? And then this simplified. Now that's the derivative part. So remember, I got to take this result now and divide it by x prime of t, which was e to the 2t, right? So putting all the pieces together, I have my x, um, my dy dx differentiated with respect to t on top, the e to the t on bottom, and that will combine to be e to the 3t on bottom. Okay, and then I just move things around one so that my um, linear form has the variable in front, but also because this is negative, so I prefer to put it in the back anyways, right? Keep the first term positive. And so that is my second derivative here. Okay, 2t minus 3 over e to the 3t. And if I want to rewrite it in more linear fashion, then I can just make this a negative power instead. I don't have to write it as a rational function, which I do prefer to do. Okay, so let's do another example. For this example, let's go ahead and find an area under a curve. Um, oh, actually, we'll do surface area. Okay, so here we're going to find the exact surface area of the surface obtained by rotating x equals 2t squared plus 1 over t. So here we're kind of doing everything right. I'm finding an integral, which is what area is. So area is a lot easier because it's just the functions, right? The surface area is an integral that has area and arc length in uh, all together. So we're just going to do the surface area example, and the rest you should be able to figure out as you come across them. So we want to find the exact surface area of the surface obtained by rotating x equals 2t squared plus 1 over t and y equals 8 square root t about the x-axis, right? So for t being from 1 to 3. So we need x prime and y prime, right? Because again, the formula is 2 pi times y of t, which we have, but we need x prime and y prime, and we need to square them and add them together, right? So first things first, let's find their derivatives, and then we can worry about squaring them and everything. So here for x prime, um, the derivative is really, really easy, right? This is going to be a 4t. This is 1 over t, which is the same thing as t to the negative 1. So we'll do, it's basically just power function. derivatives here. So 4t minus t to the negative 2. Here, this is also power function, right? This is 8 times t to the 1/2 power. So um, we'll just bring down the 1/2, which brings that to the 4. And then 1/2 goes down by 1, so that's negative 1/2. So really, really easy to do. We'll square those terms, okay? I guess we'll throw them into the formula all at once first. 2 pi, 1 to 3, y of t, which is 8 root uh, t, and times the square root of x prime squared, okay, which is 4t squared. Multiply those two things together and double it, so that's going to be t times negative t is a negative 1, and then 4 times negative 1 times 2 is negative 8, and then square those last terms, so that's a plus, and negative 2 plus negative 2 is negative 4. Okay, so that's x prime squared, or I'm going to add to that y prime squared, so this will be 16, and then when I square this, 2 times negative 1/2 will be a negative 1. Okay. So I can't combine terms with the 16s, right? But this negative 8 and 16 here gets to combine. Those are like terms, right? So this will just turn into a positive 8t negative 1, and this one will just basically go away. Okay. I can also incorporate this root t because it's a square root times a square root. So I just put it here in front. But as you can see, the inside here, we have the 16. This is now a plus. I still have this term, and then this one combined with that one made this positive. So now let's go ahead and just multiply through this t just to get it out the way. Here, my 8 moved to the outside with the 16. And so this will be 16t cubed. This will just be plus 8, and this will be negative 3. Okay. Oh, sorry, I did the opposite. I pulled out a 4, right? A t to the 4, right? So I'm going to pull out 2 to the 4. So all of these are going to increase in power, right? So this is going to go plus 4. This will go plus 4, so that'll be t cubed. This will go plus 4, so that's t to the 6. And here I have t over 2 to the 4th, which is t to the negative 3. Okay. Boom. So here, this is a perfect square. Okay, if you don't remember how to do this, you can use a u substitution where u is t cubed, right? And then you'll see here that this is very clearly uh, u squared, right? And then it's a little bit easier to be like, oh, okay, I can now factor these things, right? And so if this is a 4 and this is a 1, well, 4 times 1 times 2 is 8. So it's very clear that this is a perfect square. Okay, so I can factor it like this. Um, And then now I can apply this square root. Okay, so you might say, well, what about this negative 3? It doesn't care. It doesn't matter because it's a power, but it'll get rid of the square here. So this will just turn into t to the negative 3/2, and this square goes away. And now I just have a power of t times another polynomial, so I'll just distribute this through. So remember when you multiply, same base, it's the powers add. So this is same as 6 over 2. 6 over 2 plus negative 3 over 2 will just give me a positive 3 over 2. And this will turn into t to the negative 3 over 2. Okay. And so now it's very, very easy to integrate because now it's just a bunch of power functions, right? So we know how this works. This goes up by 1 and we multiply that by the reciprocal. So 3 over 2 plus 1 is 2 over 2. So that's 5 on top over 2, and the reciprocal turns this into 2 over 5, so this will be 8 over 5 here. This will be negative 1/2, so the reciprocal of that is 2, and we'll evaluate these at the bounds 1 and 3. Okay, we have 5/2 here. So yeah, so we just evaluate the bounds, so we'll plug in 3, and we'll subtract from that, plugging in 1. Okay. Let's see here, like I'm being a little fancy first. Let's pull out the common 2. Let's pull out this 5 on the bottom. So pulling out the 2 on top turns this into 4 and this into just a 1. But pulling out the 5 on bottom pulls out the 5 here, and it multiplies this by 5. So pulling out the 2/5 will turn this into a -5, right? So basically, I'm pulling out the 2, which makes it 1, and then pulling out the 1/5 multiplies it by 5 as well. Much easier to simplify here. This will turn into 32 over 5, but it makes this easier to evaluate for the 3 and the 1, okay? Especially for the 1, because both of these things at 1 is just 1, right? So for 1, this turns into 4 minus 5, right? So I just get a minus 32 over 5 pi here. So that's pretty nice. For 3, we'll just kind of have to look and see what that does for us, okay? So here I'm pulling out the fraction term also to make it a little bit easier for myself. So I'm pulling out the smallest one. And so now, at least for 1, right, this will just be as it is. This is -1. When I plug in 3 here, I'm going to get 3 cubed. So that's 27 times 4 minus 5 times this root, -√3. So that's 108 minus 5, okay, minus, again, just the 1, right? I'm minusing, so that'll give me a +1 here. This is just 103, and so I have 3 to the -1/2 times 103 plus 1. So again, remember this 3 is protected here because it's, what do you call it? It's a square root, right? So if I try to simplify this a little bit more, I can rewrite it in its standard form, right? 103 over √3 plus 1, 32 pi over 5. And I can't simplify anymore. So either I would finish here as my answer, or if I want to write it here, I could finish here. I can rationalize the denominator, right? I can rewrite this as √3 over √3 and try to combine those, but all of that's unnecessary. This is pretty much the either of these is as a final answer. Makes the most sense. Okay, and so that's how that works. All right, I'll see you guys on the next video. If you guys need to change this to being rotated about the y-axis, um, then you know what I mean. Just think about how does this change, right? So if I'm not going against y anymore, what is my function? What is the equivalent surface area formula look like when I have to go against the x-axis? And then how would that change this form? That's probably the easiest way for you guys to try to think about how to change this is by looking at how the other one has to get changed, right? The standard form in rectangular coordinates, and then it's applicable to change that, um, just like you had to change the surface area when rotated about the x-axis. Okay, so that's the easiest way to try to deal with if we rotate around the y-axis instead. Okay. All right, so I'll see you guys on the next video.